Howdy everybody, welcome back to Professor Carbon. In this video, what we're going to do is go over a relatively complicated arrow pushing mechanism, which is shown here. And as with all of our videos, what I encourage you to do is to take a second, kind of orientate yourself as to what the problem is, and then actually pause the video and spend some time trying to solve the problem all on your own before you just watch the solution that I have. As a reminder, that's really where the learning happens, and it's very important that you actually spend time engaging with the problem instead of just passively watching somebody else solve the problem. So with that, I'm going to just take a quick second here and ask you all to pause and solve it all on your own. Okay, welcome back. So in this problem, what we're going to do, and with all of the arrow pushing mechanism videos that I have up, what I encourage you to do is to very first look at the starting material and look at the products and look at the bonds that are being made and broken. And so hopefully right off the bat, we can recognize that there are two carbon-carbon double bonds in the starting material, which are not there in the product. And in the product, we've made this single bond here to the benzene ring. So that one's an important one. And if we count and label from the oxygen here, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, we can kind of see that this chain snakes around, and we can number everything here from oxygen 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, and it takes a second to write out all those numbers, but that really helps us understand that we also need to form this bond in the product from the starting material. And so this is kind of great. We've got two double bonds that are somehow converted to single bonds. And hopefully that gives us at least some perspective on what happens. By the way, for those of you that are in the section on electrophilic aromatic substitution, hopefully you recognize that that second carbon-carbon bond is actually formed via an EAS mechanism, or at least it should be if we're following kind of the basics of the textbook. So here we have an acid catalyst, and as always, I like to use just H+ for this. Of course, H+ doesn't come in a bottle. It comes as a complicated acid of some kind, and so for this purpose, I said, well, you can just assume it's sulfuric acid, but mechanistically, we don't really care if it's sulfuric acid, if it's triflic acid, if it's tosic acid, if it's some other complicated acid. What we really care about is that it's a proton source. And hopefully from the first semester of organic chemistry, we remember that acids are able to protonate alkenes and make carbocations. And so that's the first step in a addition across an alkene, whether it be an HCl addition or an HI addition or the addition of water using sulfuric acid. One thing that is interesting here is that we have two double bonds, and so we're going to have to consider either or both of them being reactive. And that will also lead to some of the second part of this question, which is down below, which indicates if we think critically about the mechanism above, maybe we can identify what some of the products are. And it turns out that this reaction is often much lower yielding than 100%. Often these similar reactions might be even under 50% under a lot of conditions. And so, it becomes very important to think about critically where those other pathways are that might lead to products that we don't want. Now, I'm going to start from the tertiary alkene, or tri-substituted alkene. I'm sorry about that. So let's have that grab the hydrogen. And what I always find the most challenging with some of these problems is to draw the starting material in the same way as we had it here. So I'm going to draw in that H that was added. And because we always want to make sure we're balancing our charges, if we go in with H+, we want to make sure we come out with something that's positively charged. And in this case, that's the tertiary carbocation. Tertiary carbocations are, of course, really great electrophiles. And it turns out that this alkene is perfectly situated to attack that tertiary carbocation. Now, you'll notice that we could, in principle, put the hydrogen on the other side of the alkene or on this side, and I put it over here to follow the Markovnikov rule and to form the more highly substituted carbocation. That same process is going to be followed over here. So, we could make the carbon-carbon bond from here or from here, And of course, we're going to make it from this side because that would leave behind the more highly substituted tertiary carbocation. And if we're keeping track, that H we initially added is the one over here. And if we like our numbering system up above here, we've now made a bond from 7 to 12, which is important because that's the one that's actually over here in the product. Now we have a more highly substituted tertiary carbocation, and this more highly substituted tertiary carbocation can indeed undergo then the electrophilic aromatic substitution. So for those of you that are in my class at the University of Minnesota, you'll know that I always refer to EAS as being a two-step process where you make an electrophile, and then E plus in the second step does an electrophilic aromatic substitution. And the exact steps and process of that EAS are the same, irrespective of what the actual electrophile is. In this case, the electrophile is the tertiary carbocation, and so I'm going to label this as E+. All right, then let's have our arrow attack there. And we'll notice that this ring, in principle, in the starting material, could undergo EAS at a number of spots. So we have 4 groups there. Remember, electrophilic aromatic substitution is directed by the most powerful directing group. And so in this case, that is the methoxy. This CH2 is also an activating group, but this OCH3 is going to be an ortho para director. And so it should try to be substituted at these 3 spots shown here in the darker green. And it turns out it's really hard to get EAS to go between those 2 groups. And I'll mention that here in a little bit, but that is a potential side product to consider. Thankfully, because this is a cyclization, this spot is not able to bend. And so we can't actually get the molecule to physically wrap up that way, but thankfully, this really strong donating group can help undergo electrophilic aromatic substitution at that parasite. So we can carry on with the next step here of the electrophilic aromatic substitution. And this closes up the last ring. What am I missing here? Go. And I now have an H, and then I'm going to put the positive charge over here. And then this was the H that we started with originally, all the way back at H+. Now from here, we can just have this hydrogen come off and reform that double bond. Ta-da, product. I understand some people are less comfortable with H+ coming off into the vacuum. And so if you prefer, you're welcome to draw bisulfate being the base to help facilitate that proton coming off. In which case you would have your acid catalyst be reformed. Okay, so that completes the arrow pushing mechanism. It started with a acid addition of H+ to an alkene, just like any old alkene addition would begin. That tertiary carbocation then is attacked by another double bond to generate a second tertiary carbocation. And then that second carbocation functions as the electrophile for an electrophilic aromatic substitution pathway, which of course is a 2-step process whereby the pi electrons attack the electrophile, and then the electrophile or the complex loses H+ to reform the aromatic product. All right, so this is great. The follow-up question here then is, because this reaction is less than 100%, what are some things that could go wrong? And it turns out in this reaction, there is a lot that can go wrong. So I'm going to grab the green marker here to be able to talk about all the things that can go wrong. Well, the first thing that could go wrong is, we had that terminal alkene, the one dangling out over here, undergo the first protonation. But what if this internal alkene undergoes the first protonation? Well, that would generate a very similar tertiary carbocation, but it would have an acyclic tail. And so that for sure could make a monocyclic product via the same electrophilic aromatic substitution. Oops. Yep, and I think that'll be our product there. So you should have just one cyclization because it started from the undesired alkene. And there's not really a great way for this product to then go and form the desired product. It's kind of stuck being at the wrong product from there. You've noticed that we have this this OCH3 group and a number of all of our intermediates and starting materials. And of course, the acid hydrolysis of ethers is something we could consider. And I'm just going to put a squiggly chain here for what the rest of that ring is. And we could just imagine cleaving that OMe to be an OH. Turns out that's not a super big byproduct, but it's one that we could consider. As I alluded to up here, we could also imagine the wrong site undergoing the electrophilic aromatic substitution. And again, it turns out for steric reasons, this is not the most likely product that will form from this pathway, but it's one that we could at least consider having as a possibility. And the reason that it's not really a big problem, which you might be able to see from the way I'm struggling to draw this, is that there's a good amount of steric clash between that ortho CH3 and what approximates a tert-butyl group. So at least this bond here is a quaternary carbon formed from the tertiary carbocation, and that generates a lot of steric clash. And so it's hard to squeeze that big group in between the other two substituents. Nevertheless, it is a byproduct that we could consider forming. And probably the cause of the most byproducts, if you will, is the nature of these carbocations. And we have not only one, but two carbocations in this mechanism. And for the students in my class, I always remind you or encourage you every time you draw a carbocation to consider it being captured by a nucleophile, even if it's not the nucleophile you want. It could undergo some kind of carbocation rearrangement, and every carbocation that has hydrogens next door can always eliminate via some kind of E1 pathway. And so both of these carbocations could in principle form alkenes. Now, the good news about those is that if we protonate them again, we might be able to re-engage in the cycle. And so one example of that, which is for sure an issue in the experimental reaction, would be to have it be kind of a monocyclized intermediate where we have that methyl group. And then depending on which hydrogen is eliminated, you could have a double bond between any of those sites. And sometimes it's even represented with these sort of dashed lines because it arises from this tertiary carbocation losing this H, or this H respectively. And ideally that would follow the Zaitsev's rule where you form the most highly substituted alkene. And so that should be predominantly the up-down one here in between, but that might not be universally true. And you might end up with a mixture of some of them. So there's up to 3 different alkenes represented by that one structure. So with that, we can have 3, 4, 5, at least 6 byproducts that we can consider. And last of all, don't forget, we do chemistry in Avogadro's number of molecules. And so there's always a possibility instead of cyclizing that it reacts with a nearby molecule. So if you run this reaction at high concentration, the speed at which the neighboring alkene attacks that carbocation might be the same as having an adjacent molecule or a neighboring molecule engage. And so polymerization is a problem or a possibility just as much as intramolecular cyclization. And so you can see here that there are a wide variety of things that can go wrong in what looks like a fairly straightforward cyclization, electrophilic aromatic substitution. But these problems are what make organic chemistry quite fun and very challenging to get good results in the lab. And that's what makes the field very interesting to try to master. So with that, hopefully you've enjoyed this Professor Carbon video. As a reminder, you can find the content that you're looking for on the banner. They are color-coded by both topic and problem style. And so please take a look at the other videos or play one of our playlists that fit the content you're looking for. So thank you and have a great one.